Welcome back to ECE 320A. As a reminder, your next homework assignment is due next week at this time. Well, maybe a few hours after this, so maybe not quite a week away, a little bit more than a week. But your next exam, just to put it on the radar screen, is 3 weeks from today. It's the 24th of October, just to let you prepare for that, and there probably will be 2 more homework assignments beyond homework number 3 in that time interval. And most of the material that we will be dealing with will be the Laplace transform, and I want to try to provide you with a big picture perspective on the Laplace transform. Then we'll have a quiz. Boy, tough audience. Then we'll develop some operational transforms based on what we learned from the quiz. And that will actually allow us to expand what we can Laplace transform, or what we can do with the Laplace transform. Hopefully we will get into circuit analysis with the ladder technique. Have you guys learned that already? The ladder technique for circuit analysis. Does that sound familiar? All right, maybe that will be something new that you haven't yet seen. And if we get there, we'll start inverse Laplace transforms. And this is, okay, it's a big picture. It's not the big screen, although it is a big screen. You can sit back and kind of watch this movie. I'm just going to scroll through this information, and then we'll get into maybe paper and pencil ideas. But I want you to get comfortable with time domain and frequency domain. We're dealing in the 2 domains, and I want you to get comfortable going back and forth between those. In this class, those 2 domains are related to each other by the Laplace transform, which is indicated in red. That's the definition of the Laplace transform, and that allows us to map these signals in the time domain, f of t, into a compact representation in a different form, but it's now giving us that information in the frequency domain. And because we're dealing with the single-sided Laplace transform, which is really key, we're starting it at time t equals 0, that allows us to have a unique relationship between the f of t and the capital F of s, and we can actually go the other direction. And we will go the other direction in this class really by just matching up pairs. That's why transform pairs are so important. If we know how to go from f of t to f of s, then if we see an f of s, we can immediately find what it should be in the time domain. That's the idea. In this class, we're looking at the Laplace transform via circuit analysis. But it leads to a lot more things. It'll immediately give rise to transfer functions. For example, we can analyze a RC circuit and find its transfer function, which might give us this transfer function, 10 over s plus 10. That's a low-pass filter. We can then look at that transfer function and identify poles and zeros of that transfer function. What values of s, what finite values of s cause the denominator to vanish or to equal 0. Those we call poles, and those are our x's in our diagram. What finite values of s cause the numerator to vanish. Those we call zeros. In this particular low-pass filter, there are no finite values of s that cause h of s to vanish. So somebody might say, well, there's an infinite 0. What's an infinite 0? An infinite 0 would be when you let s go to infinity, then h of infinity does go to 0, doesn't it? As you let s get really, really big. That's why we specify, usually when we just say poles and zeros, we're talking about finite values of poles and zeros. But I've qualified that here, saying there's no finite zeros. But if somebody says, oh yeah, there's a 0 for h of s, okay, they're including the infinite 0. Once we have transfer functions and poles and zeros, we can be thinking about Bode plots. This green line that's flat, and then it starts sloping at a slope of minus 20 dB per decade. What's a decade? In years, what's a decade? 10. So we'll be using a decade as a factor of 10. We will also talk about octaves. What's an octave represent in terms of a multiplication factor? You have 8 keys, maybe 8 white keys on the piano, so you want to think 8, but it's actually a factor of 2. So we'll talk about octaves and decades, and we'll use those interchangeably. Consistent with minus 20 dB per decade is minus 6 dB per octave. And it may be more important to shorten up our range or our interval to just 2 times or a factor of 2 instead of a factor of 10. That's why we might want to talk about octaves or versus decades. But this is now a frequency response, and if you don't see it, just go to your stereo. If you have a graphic equalizer on your stereo, you've set those knobs. The bass is maybe here, and now the treble is at the same place, and the high frequency, oh, it's troublesome. So let me lower it. And now you have those knobs giving you the low-pass filter behavior. And the vertical axis is in decibels, which is 20 log the magnitude of the transfer function. So that's why I have this vertical bars around h of j omega with a subscript of dB. That's decibels. That's the units on the vertical axis. Again, we'll get to all of this, but this sort of tells you where we're headed. Once we've seen Bode plots, poles and zeros, now we can start designing low-pass filters, high-pass filters. Those prefer high frequencies. Band-pass filters, those like to pass frequencies in a certain band, and these are the magnitude plots of those. Band reject filters, where we might try to attenuate certain frequencies. Maybe we have 60 hertz hum coming in, and we try to notch that out. We might like a notch filter at that particular frequency. Or, now I won't say anything more about band reject. I will say, though, that the Laplace transforms are more powerful than just circuit analysis. So don't just assume that since you're learning about these techniques in a circuit class, that it only applies to electric circuits. You can apply this in electrical systems, mechanical systems, electromechanical. Electromechanical is like a machine or a generator, where you're maybe converting between 2 different types of energy, electrical and mechanical. Thermal, maybe you're trying to model something's temperature distribution or the dynamics of this particular system's temperature. Chemical, optical, etc. All of these can be modeled via the Laplace transform, and you can use transfer functions to help you better understand. So if you learn it well here, now if somebody starts getting up at the board and they're talking about some mechanical system, and here's the transfer function, you're going to go, I know what he's talking about. I can see that mass spring damper system as an RLC circuit. That's an analogy that you could then use to get comfortable with this new terminology. Pictorially, we have this time domain picture where we inject the input signal into our circuit. For our situation, it might be a mechanical system, it might be an electromechanical system. And that produces an output. Have you had convolution yet? Some of you will learn convolution. But that's just this integral that essentially weights the input as it passes through the system. The system here is modeled by an impulse response H. And I think last time I talked about the impulse response. What happens when you apply an impulse to a system? It produces the impulse response of that system It's like hitting your, this doesn't vibrate. It's pretty solid. It shakes, it moves a little bit. Not much, but not as much as my hand. But it does move. So you hit your electrical system with an impulse that energizes all the energy storage elements, and then they start to decay. And you can watch that. That's the impulse response. You can then use that for all sorts of inputs to generate an output. Maybe you want to see what's going to happen for a step input. You use x of t equal to a step. Maybe you want to see what it will do for a sinusoid. You use x of t as a sinusoid, and you can plug it into that integral to get the convolution or the output. You can also solve the problem, meaning these two red brackets are connected by the Laplace transform. You could jump into the frequency domain and analyze the system in the frequency domain. You would Laplace transform your input signal, little x of t, and generate a capital X of s. You would analyze your circuit. Maybe you have a differential equation. You convert that into a transfer function in the frequency domain. Now you have a capital S H of s that models your system. Now to generate the Laplace transform of the output, you simply have to multiply these two ratios of polynomials together to generate another transform expression. And to get back into the time domain, you just have to know your transform pairs. And you can go from capital Y of s back to a Y of t. And then you're done. But this allows you then to think about what does your system do? H of s, you could think of that, oh, you have the frequency response of your system. You have the Bode plot. Now you know how that system favors certain frequencies. If you know what the frequency content of your signal is via capital H of or X of s, then you can understand what's going to happen at the output. All right, the movie's over. Now to the quiz. And if you're following along with your textbook, this is table 12.1 or some of table 12.1. If I now give you an impulse, we've already derived this. Do you remember what the transform, the Laplace transform of an impulse equals? If little x of t is the impulse, what's capital X of s? Right? Your sifting operation, and that gives you a 1, doesn't it? That's the Laplace transform of an impulse. What about the Laplace transform of a unit step? One over s. You want to be very comfortable with these transform pairs so that you can, when you see some of these factors, you can immediately go back and forth between the time domain expression and the frequency domain expression. What about an exponential decay? What's the Laplace transform of an exponential decay? Do you remember that? That was buried in an earlier table when we were deriving the transforms of a sinusoid. But here, let's say that you just have an exponential decay, e to the minus 4t, and you want to determine what's its Laplace transform. Do you remember? So we were looking at e to the minus gamma t. Do you remember that? And we found that that was 1 over s plus gamma. That's all we're doing here. If we have an e to the minus 5t, then its Laplace transform would be 1 over s plus 5. And you should now instantly see where is the pole associated with that capital X of s. What value of s causes that denominator to vanish? Minus 4. And that's a well-behaved signal, isn't it? It's in the left half complex S plane. It's e to the minus 4t. What about a sine wave? And it's critical that we're turning these signals on at time 0, or at least we're turning them on. They're not happening for well, it could happen for an infinite amount of time after you turn it on, but we're not looking at the negative infinity to positive infinity duration. Here we're turning it on at t equals 0, or let's say t equal 2, or t equal 16.7. We'll turn it on at some point. What's the Laplace? So this, I want you to get comfortable when somebody multiplies a waveform by the unit step, they're using that unit step as if it was a switch. This u of t is only 0 or 1. It's 0 whenever the argument is less than 0. So it annihilates this for all values of t less than 0. When you turn that switch on, when t becomes non-negative, u of t equals 1, and that's like just saying, oh, x of t is sine of 5t for non-negative values of time. This top bracketed expression is equivalent to this lower expression. And sometimes you'll see it written either way, but you need to be comfortable that it's meaning the same thing. Do you remember what the sine wave was for its Laplace transform? Okay, it's omega over s squared plus omega squared. What's omega in this example? 5. So now we have omega 5 over s squared plus omega squared, which is 5 squared. Questions on that? If I gave you sine of t, then what would capital X of s be? If I just gave you sine of t, 1 over s squared plus 1. Your omega is 1 in that example. Cosine. Again, we're using the same notation. It could be either cosine times the switch that turns it on for non-negative values of time, which is u of t, or we could give it this sort of 2-row formulation for x of t and indicate when it's negative or when it's non-negative time. What's this transform look like? What's the denominator look like for this one versus the sine? They're the same, aren't they? They're sinusoid that's at the same frequency, so their poles are at the same location. The difference between the sine and the cosine appears in the numerator. What's in the numerator of this transform? It's the frequency variable s. It has a finite 0. The sine does not. And now if you have some expression in the numerator, let's say you have 4s plus 10 over s squared plus 25, that's s squared plus 5 squared, then you have some combination of sine and cosine in your time domain expression. What about these signals? If I now gave you x of t equal to cosine 4t minus 6, and now I'm throwing the switch on at time t equal 1.5. That's a little different than what we've looked at before, isn't it? Before, our argument in the cosine was just omega t. Now it's omega t minus some delay. or some phase shift. We now need to parameterize that number, this minus 6, as some amount of the frequency. In this case, the frequency is 4. We need to see what 6 looks like when we compare it to 4. We need to factor out an expression so that we can sort of say, well, what's the cosine look like when we turn it on at u of t minus 1.5? The second one, these aren't equivalent. The second example is, okay, I know how to transform a cosine, but now you've exponentially decayed that cosine. Now you have some signal. Didn't give myself enough space, but it looks more like that. It's a cosine that gets damped by e to the minus 4t. What's the transfer function of that going to look like, or the Laplace transform of that? And that's why we need these operational transforms. We'll look at 3, and I'll just state them now, and then we'll go back and use those. The first one we've really already derived, I think, from the formula of the Laplace transform. Translation in time. F of t minus t naught, u of t minus t naught. F of t, we know it's Laplace transform. That's capital F of s. If it's shifted in time, then in the frequency domain, that's just multiplication by e to the minus s times the amount of time delay t sub 0. So if we knew the f of t, capital F of s relationship, we can immediately find, and look, this u, the switch, is exactly the same argument as the waveform f. And that allows us to then say, oh, we know how to Laplace transform that expression. Not only can we translate in time, we can translate in frequency. Here's how we will address that second example. If I know the Laplace transform from f of t to capital F of s, if somebody now just exponentially damps that waveform, all I have to do is go over here and change every s in my expression to s plus a, where a is this amount of damping in my exponential decay. So if you have the expression for a cosine, and now you hit it with an e to the minus something t, you can immediately find its Laplace transform by using this translation in frequency transform, or operational transform. And finally, we will go through scaling. If we scale the time axis, if we make the time axis stretch, if you thought you might have a sine wave in between my hands, and now I stretch my hands, the maximum and minimums on that sine wave are going to do what? If they were here, and maybe I had 5 bumps, and I still have 5 bumps, what happens to those bumps? They get wider, don't they? So in terms of the time axis, you expand the time, what happens to the frequency? It's reciprocally related, isn't it? It's going to go down. It's not going to be happening as often. And that's what this is saying. We have AT, then in the frequency domain, we divide the S by A. S and T are reciprocally related. All right, let's go through some examples. Now we can start taking the notes maybe a little bit more carefully. Well, maybe I won't be talking anymore. We'll just do it with gestures, hand gestures. What's the Laplace transform of little x of A? I think we've just done this in our table, didn't we? Now we have a cosine that we're switching on at time 0. And we could write that either way. You might see it written on the right, or you might see it as multiplication by the unit step. But it's the same. It's an equivalent expression. What's capital X sub a of s? It's a cosine, so what's in the numerator? S. And what's in the denominator? S squared plus omega squared. And that gives you poles right on the imaginary axis, which means there's no decay. It just continues to shake at 4 radians per second. All right, we're working our way through this to try to introduce some delay. What if we now looked at the following? What if we had x sub b of t equaling cosine of 4t minus 6 for t greater than or equal to 1.5 and 0 for t less than 1.5? Or I could rewrite that Is it clear what that means? I actually tried to generate some MATLAB sketches of this. Let's see if this will help. Here's a cosine waveform of 4t up above, and it's happening for all time. Obviously, I can only show a finite length of time interval from -5 to 5 is what I selected. That's cosine of 4t. If I turn that on, if I switch it on at 0, this is what x of t looks like. Right? And that's the kind of signals we want to Laplace transform, is the one below. We're not assuming that this cosine is happening for all time. We're just looking at signals that are one-sided, that only start at time t equals 0. And then we look what happens. What if I now take that cosine of 4t and I delay it by 1.5 seconds? Or I don't turn it on until, so I have cosine of 4t, but now I want to turn it on at 1.5 seconds. So I would just have the entire x of t, and then I just erase everything before t equal 1.5. And this is now what we want to Laplace transform. If you looked at the bottom picture and compared it to the top picture, most of it looks the same, doesn't it? It's just there's a small delay between the bottom and the top, but pretty much they're very close. They're very similar. What we need to do then to find x sub b of s is we need to make sure that we can try to match up the argument of the cosine with when the switch is happening. The switch is happening at 1.5. So we now need to figure out, can we write that cosine expression as some cosine that's delayed by 1.5 seconds? So if we look at the argument of the cosine, this is now 4. I'm going to factor that out of both pieces. But 6 over 4, wow, magic, huh? So that argument in parentheses looks like when I turn it on, meaning I now can rewrite x sub b of t as cosine of 4 times t minus 1.5 u of t minus 1.5. And the important thing is that this piece is the same as that argument. And now I can go back to my translation in time operational transform. I now have a cosine with a t that's delayed, t naught, and it's being turned on by that same amount of time, which says that my Laplace transform if you wanted to get 2 points out of 100 on the exam, you would at least write down the cosine's Laplace transform, right? If you go, oh, that's delay, I don't remember how to do the delay. But what's the frequency? 4. That's not impacted by the delay, is it? So now you know the denominator is s squared plus omega squared. And how's a cosine's numerator structure? Just the cosine. Don't worry about the delay. That's just s, isn't it? So now you go, well, I know that's not quite right, but it's got to have this structure to it, and it's maybe weighted. Now you just have to go up to the operational transform and realize that the delay is t naught. In this case, it was 1.5. We put in 1.5 for that t naught. That scales our nominal transfer function. And that's now our Laplace transform of that weird-looking time-delayed cosine waveform that had a frequency of what? Well, if I just gave you this Laplace transform and said, what's the frequency of the cosine or sine wave associated with this transfer function, you should be able to tell me. You can say, oh, the poles are at plus and minus j4. Your frequencies are 4 radians per second. So your sines and cosines, whatever those would be, are going to be 4 radians per second. All right, that was maybe too easy. Let's look at another one. Suppose we give you x sub b again. No, let's try x sub c of t. Suppose the third example is now cosine of 3t minus 5 times u of t minus 1.5. Oh, shoot. You factor out the 3 from that 5, and what do you get? Do you get something that's related to 1.5? No. It's a curveball, isn't it? That's an exam question. So what do we need to do? Well, if we just go back to the pictures, this is actually what it will, this is what it looks like. The top one I just started it at -1. It should be going, the MATLAB, and I didn't worry about the scaling. It just decided to make its axis, its horizontal axis, start at -2. But that waveform is for all time, up above, on the top one. Then I simply start it at 1.5. That looks very familiar, doesn't it? Looks like a conventional cosine waveform. So we know the main piece of the Laplace transform for that waveform just by knowing that it's a cosine and not worrying so much about its delay. This is what it looks like. You just have a cosine whose argument is maybe messed up a little bit, or it involves a phase shift, and now you have it turning on, or somebody throwing the switch at some non-multiple of that phase shift. That just means they're playing with the origin in time relative to where they put time t equals 0. So now if we go back, what we want to do is look at the argument of the cosine and see if we can create a piece that looks like t minus 1.5. The cosine's argument is 3t minus 5. Well, if that wasn't 5, if it was 4.5, I'd be happy, right? Because 3 I can factor out of 4.5, and I'll get 1.5. Well, 5 I can just write as 4.5 plus a half, right? And that's what I'm going to do. Now I'm just going to say, well, I'm going to change, or not really change, I'm just going to rewrite the argument in a slightly different structure. I'm going to say now that I'm going to replace the argument expression with 3 times t minus 1.5 minus 0.5. Where this, well, that's the piece that I wanted, wasn't it? And now I've created that piece that I wanted inside my cosine argument. I can now rewrite this cosine, x sub c of t, as the cosine of 3t minus 1.5 minus 0.5 u of t minus 1.5. Is that better or worse? Feel like we're at the altar, for better or for worse? Where'd that come from? Oh, that came from one of these papers. If you didn't come early, you missed that story. Sorry. Where were we? Oh, 320. 328. We need to Laplace transform this cosine. How are we going to do that? If that minus a half wasn't there, we'd be okay. This is why you have to go back to your 4th grade trigonometry class and remember how to convert cosines, right? Or the sum of cosine angle, cosine of a plus b. Meaning, if we put this piece and say that's a, and then we take this piece and say it's b, or maybe we incorporate the sign. Maybe I want to do that. That's b. So that if I go back, if you're following along in your textbook, that's in Appendix F, which is page number 759. I believe it's the second trig identity says that the cosine of a plus b, and maybe you have this memorized, do you? It's Been a while since 4th grade. I'll give you that. There we go. Now we can use this to end up with an expression that we will be able to work with. So that now if I say, okay, I want the Laplace transform of x sub c, I want x sub c of s, which is the Laplace transform of this cosine of 3 times the quantity t minus 1/2 minus 0.5 u of t minus 1.5. But now I'm using this piece as b and this piece as my a in the cosine of the sum of two angles, cosine of a plus b. That allows me to then conclude that I can say, well, that's just the Laplace transform of cosine of a cosine of b, and I still need to weight it by, or turn it on at time 1.5. And now I subtract from that this product of sines. The sine are we any better off? Did we just make it even messier? What's cosine of 1/2 or minus 1/2? And here you need to make sure on your calculator you're using the right argument for cosine. If you've set up your default mode to be in degrees, you don't want to be thinking that that 0.5 is 0.5 degrees. It's 0.5 radians because it was the argument inside the cosine. And we had t in there, which was seconds, multiplied by frequency, which was radians per second. So radian per second times time gives you radians. What's left over is a radian unit, and that was the 1/2. How big is a radian in terms of degrees? You have 2 pi radians in 360 degrees, right? So it's about 58 degrees, 1 radian. And we want half of that, 27 degrees, 28 degrees. We want the cosine of 28 degrees. And that will just be a number. This is just some scaling factor now, isn't it? As is the sine of minus 0.5. This is just a number. And that sine of minus 0.5 is another number. And those can be factored out of the Laplace transform operation. The Laplace transform is a linear operation, which now allows us to say, oh, now I can write this as cosine of minus 0.5 times the Laplace transform of the cosine of 3 t minus 1.5 times u of t minus 1.5 minus, well, let's take out the minus inside the argument of sine, since sine is an odd, so we'll say plus sine of 0.5 Laplace transform of sine. Is it clear what I've just done? I've now eliminated that ugly delay mismatch with the switch delay, and now I simply have two Laplace transforms that look like my translation in time operation. I have the argument of my cosine the same as the argument on my switch. I have the argument of my sine the same as the argument of my switch. Yes. So what I did in that last line is I took sine of minus x, okay, to make that minus sine of x. Are we okay? Now can we get the Laplace transform? I now have the cosine, and the cosine's an even function, so I'll go ahead and just get rid of that negative sign in the argument. What's the Laplace transform of that first bracketed piece? What's the frequency? What's going to be in the numerator? Do I need to scale this by anything? So if you're going into the frequency domain, your final result shouldn't have time in it, shouldn't have any t's, and if you're going the other way, you should be getting rid of the s's and putting back t's. So that's sort of a way to check your work. So that's an e to the minus 1.5 s. In the time domain, we have these decaying exponentials. Here, this is a complex exponential in the frequency domain. That s is a complex number. Are we comfortable with that half of capital X sub c of s? What's the last half? The sinusoid is at exactly the same frequency. My denominator expression looks exactly the same, s squared plus 3 squared. What's in the numerator? And if you actually wanted values, you could say, well, that's 1/2 times 180 degrees over pi. Now I can plug that into my calculator. This is the sine of 28 degrees ends up being a value of 0.4794, and the cosine of 28.6 degrees. And now I just have those scaled values of those Laplace transforms. Is that okay? Now you know how to use the translation in time operation or operational transform. Let's look at the next one. Which is operational transform number 2, which was complex frequency. Complex frequency variable translation theorem, which said if I have an e to the minus at f of t, if I knew what f of t's, little f of t's Laplace transform was, if that was f of s, then when I weight that by a complex exponential, everywhere I had an s in my original Laplace transform, I simply substitute s plus a, and I have my new Laplace transform. Why did that happen? If we simply go back to the definition, and if we look at e to the minus at, f of t, that's now my signal that I'm trying to Laplace transform. I weight that by e to the minus st, and I integrate time out of that expression. That's my definition of the Laplace transform of an exponentially damped function f of t. But now we can combine our exponentials, can't we? The exponents in our exponential. So this now becomes the integral from 0 minus to infinity of f of t e to the minus f. Uh-oh. For some reason, I knew that was going to happen today. Well, what does that give us? Besides a headache. We now have f of t, wherever that went, that disappeared. I thought I had already written that down. I'll have to go back and watch the recording. I won't be able to sleep tonight, so I'll watch the recording. E to the minus. Does that look okay? I haven't changed anything. I've just rewritten it in a different form. But what does that expression look like? Doesn't that look like exactly the Laplace transform expression if I simply replaced every s with s plus a? So this is now f of s plus a. I don't know why I'm playing with this. Oh, we're having fun, aren't we? All right. So let's look at one. This page has changes. I bet it does. That impulse response is going to hit this tablet. All right. Some of you got that joke, I guess. And it may not be much of a joke. What's the cosine of omega t? Okay, it wasn't hard, was it? Can't do anything hard now. The computer won't cooperate. So now what if I do the following? What if I say I want e to the minus 4t cosine of 3t? And I'm assuming that this is starting at time t equals 0. If I don't write that switch, that's what we're assuming. With our frequency translation theorem, wow. We now simply replace s everywhere with what? Is that clear? So now we know what an exponentially damped cosine's Laplace transform looks like. It looks similar to the cosine, except now we have this s plus a quantity squared factor and not just the s squared. If we looked at the first one, wherever it was. Suppose now we said, okay, here's cosine of omega t. That's in the time domain. And in the frequency domain, where are the poles of that transforms? Where are they going to be located? Now I'm looking at the poles of this transfer function. What values of s cause that to vanish or to equal 0? They're imaginary, aren't they? J omega and minus j omega would cause those values of s would cause that to vanish. So I have something at j omega and something at minus j omega. Those are the poles, and there's actually a 0 right there. But what about this other one? E to the minus 4t cosine of 3t. Pictorially, we could think of that as having a cosine. Oh boy, that's supposed to be a constant frequency, but it's not. Very good drawing. And then you have this exponential decay envelope of e to the minus 4t. And if you multiply those two together, term by term, you will see that you now have this decaying exponential, that red line. That's the waveform as a function of time t. In the complex S-plane, where are the poles for the transform of e to the minus 4t cosine of 3t? We now look for values of s that cause that denominator to vanish. And this expression is written in a very nice way for understanding where those poles are. That's your assignment for this evening, is to go home and show that a value of s equal to minus 4 plus j3 will cause that to vanish. And a value of s equal to minus 4 minus j3 will also cause that to vanish. They're at exactly the same vertical distance as the cosine of 3t. If this is now j3, and this is minus j3, and this is minus 3, and let's say this is minus 4, you have poles now at minus 4 plus and minus j3. Okay? And you have a 0 at minus 4. But where are those poles in this picture versus the poles on that picture? They're in the negative left half plane, don't they? And they correspond to this decaying exponential, e to the minus 4t. It has a negative exponent. In the top picture, what's the exponential decay in the top picture? E to the what? 0t, right? There's no decay. It just keeps going and going. And it's right on the imaginary axis. That's a pure oscillator. You give it a kick, and it just shakes forever. There's no exponential decay. If you move those poles into the right half plane, what would the exponential look like? E to the plus 4t. Then it's blowing up with time, and I can't shake that way. I don't want to shake that way, right? Because in a little bit of time, you would be gone, unbounded, right? You don't want to see that. Would not be pretty. Not that the exponent, well, never mind. Okay. Any questions on that? Is that helping? Well, we'll see if the computer continues to help. We have one more operational transform, and that was the scaling theorem. Which said that if we have f of t and we change the time axis, we either expand it or we compress it. But we always keep a positive, let's say. Then this transforms into 1 over a f of s over a. And you know what I'm going to ask now. Right? Now you can show this from the definition of the Laplace transform. You know that you can simply substitute the waveform, the signal that you're trying to compute its Laplace transform for, into that location in the integral, scale it by e to the minus st dt. That doesn't look like what we're used to seeing, does it? Because we like to have just an f of a single argument, not at. So let's change that. Let's just call it tau. Then anywhere else we see a t, we'll have to replace that with t over a, or tau over a. And d tau is just a dt, so anywhere we see a dt, that's just 1 over a d tau. If we use those, and now if I integrated from t equals 0 minus, where's tau starting? If t is 0, what's tau? 0. If t is infinity, what's tau? A was positive. That's infinity also. So we haven't changed the limits of integration. Our f is now only a function of tau, e to the minus s, but we don't want t anywhere, so we replace that with what it's equal to, which is tau over a. And dt, we get rid of it by dividing d tau with a. And now that 1 over a is independent of tau, it can come out front. We have this integral from 0 minus to infinity of f of tau e to the minus s over a tau d tau. And now this would look just like what we're used to seeing, scaled by 1 over a, if we simply replaced s everywhere with s over a. That's where that frequency scaling theorem comes from. And one way to sort of keep track of this, t and s, you have this e to the minus st. Well, you want that exponent to be dimensionless. T we know has units of time. So the product of st, if it's dimensionless, s is what? It's 1 over time, isn't it? So it's a frequency. These are reciprocal quantities. That's how you can sort of think of s as being a frequency. It gets when it multiplies t, you get a dimensionless quantity, which says then that they act in inverse relation to each other. If you expand the time axis, you stretch it apart, then what happens to the rate of change? Your frequencies get lower, don't they? If you did just the opposite, if you compressed the time axis or contract, now the number of maximum in that interval or in the same length of time allows you to say that you now increase the rate of change. Questions on those three frequent or operational transforms. Now you have this table of Laplace transform pairs, table 12.1. Table 12.2 gives you transform operations that you can use to expand the possibilities for doing Laplace transforms. Now that we have that, let's go back and see if we can start analyzing some more circuits so that we can get some more transfer functions or capital H of S's. We know how to do the signals. Let's now figure out how to analyze the circuits. And what I want to show you is ladder analysis, and maybe that description will make more sense. We'll just do it by means of an example, and let me just show you the circuit before I start trying to explain where this ladder comes from. Now, if somebody gave you that circuit on an interview and they said, tell me something about this circuit without solving it, what would you start telling them? Or how could you start describing this circuit in fairly general terms, but yet still extracting some of the useful information about its potential properties? It's RLC, isn't it? There's two energy storage devices. What's that tell you? If you have two energy storage devices, you have one capacitor and one inductor. You could have two inductors and you'd still have two energy storage devices. You'd have two capacitors. But now you have this possibility of things going back and forth. And what's the order of the system that you're expecting? Second order. So you could say, okay, I'm just going to assume this, or this has two energy storage devices. It will lead to a second order differential equation. Let me just talk to you about the different types of behavior you can have for a second order differential equation. And you didn't even have to solve anything. But let's solve something. Now, where did the ladder come from? Everybody familiar with a ladder? Tough audience. Picture a ladder on its side, and now you have the rungs that are these vertical. There's a capacitor, a resistor. What we're going to do is we're actually going to climb that ladder from the output towards the source, towards the left. We're going to go up the rungs of that ladder. And what we're going to try to avoid is writing three coupled mesh equations, for example, which could get ugly. Then we would just turn the crank and get an answer, and we'd go, I don't know if that's right or not. I don't know. I may have made a mistake. But the ladder technique allows you to sort of follow your work as you go. And here's what we want to do. And this can be done in the time domain or the frequency domain. We're going to do it in the time domain today. But what we want to do right now is develop a differential equation relating the output voltage, let's say V sub C of t, or the voltage of that capacitor, to the input source, V of t. And we weren't told what V of t was. We don't need to know what it is. You just give it to us at the end. All right, here's our ladder technique in the time domain. And what we want to do is start with variables on the right of our ladder and follow those all the way up the ladder and keep track of those as we go, as we start walking. So this will be in the time domain, but it can also be used, the same technique, in the frequency domain. What have I not mentioned? And I've already got a capacitor. Ice. So now you're further into the interview and you go, oh yeah, I need some ice. The interviewer's going, I don't know. Thought we were interviewing an electrical and computer engineer. He's talking about ice. All right, so how do we use ice? Well, that tells us how to relate the current through that capacitor and its voltage, which says that we know what? I says I sub c is c dv sub c dt. We know V sub c. That's just V sub c. Now, if somebody wants to know what's the current through the capacitor, we know what that is. That's I sub c, which is, in terms of the output capacitor, is c dv sub c dt. What if somebody now wants to know this current, I sub R1? Can we express that current in terms of the output voltage? R1 is in parallel with C, isn't it? So they share the same voltage. What's I sub R1? Is that okay? Now, what if I wanted I sub R sub 2? I already know I sub R1 and I sub C, don't I? And those are in terms of V sub C. So now I know I sub R sub 2 in terms of V sub C. I know that I sub R sub 2 is I sub R sub 1 plus I sub C of t, but that's just V sub C of t over R sub 1 plus C dV sub C dt. And I now know what I sub R sub 2 is in terms of the output voltage. Shoot. But we know what the voltage across R2 is, don't we? This is now plus V sub R sub 2 minus. And now we know how to relate that to this voltage. Do you see what I'm doing? Once we know v sub r sub 3, so v sub r sub 2 is what? I sub r sub 2 times r sub 2. We know that in terms of v sub c. V sub r sub 3 is now v sub r sub 2 plus v sub c. We know that in terms of v sub c. Once we know the voltage across R3, we know it's current. Once we know that current, we know I sub r sub 2, we know the current through the inductor. Now we can call up Eli. Eli tells us the voltage across that inductor, doesn't it? V is equal to L di dt. We differentiate that I sub L equation. Now we have V is a sum of V sub L plus V sub R sub 2 plus V sub C. We're up the ladder. And we can actually get back to the end because we have it all in terms of V sub C. We'll pick up at that point. You can do that tonight to impress your roommate, and we'll get started on Tuesday.